How did the Ariane 5 bug lead to disaster? Imagine watching a rocket launch and suddenly everything goes wrong in just seconds. That's exactly what happened with the Ariane 5 rocket. Let's explore how a tiny software mistake caused such a big failure. The Ariane 5 rocket used software from the earlier Ariane 4 model. This software had been tested and worked well before. But Ariane 5 had a different flight path and higher speeds early on. The software contained a calculation involving a variable called horizontal bias, which in Ariane 5 reached larger values than it was designed for. This mismatch was not caught during testing or development. The real problem started with a data conversion. The software tried to change a 64-bit floating point number into a 16-bit signed integer. Because the value was bigger than what the smaller data type could hold, it caused an overflow error. Think of it like pouring too much water into a small glass. It spills over. This overflow caused the software to crash or halt unexpectedly. The software did not have enough error handling to manage this overflow. Both the main and backup inertial reference systems stopped working. These systems were supposed to provide precise position data. Since both failed, the main computer received faulty information. Instead of recognizing an error, it interpreted the data as normal flight data. The main computer then sent commands to the rocket's nozzle actuators. Because of the incorrect data, the actuators moved to full deflection. This sudden and extreme movement made the rocket veer off course very quickly. The forces from this movement were so strong that the rocket's boosters separated from the main stage. The onboard self-destruct system was triggered to prevent further damage or danger. The disaster was complete in just a few seconds. From a debugging point of view, this incident teaches us many lessons. First, software must be tested under all possible conditions, especially those that are different from previous versions. Second, error handling must be robust enough to catch and manage unexpected situations like overflow errors. Third, having redundant systems is not enough if they share the same vulnerability. Both systems failed because they relied on the same flawed software. Fourth, diagnostic data must be transmitted and interpreted correctly. The main computer misunderstood the error signals, leading to the wrong commands. Finally, reusing software from older models requires careful review and adaptation. The Ariane 5 software was reused without considering the new flight profile. Proper validation and testing could have caught the overflow problem before launch. In summary, this disaster shows how a small bug in the code, if not caught early, can cause catastrophic failure. It emphasizes the importance of thorough testing, good error handling, careful software reuse, and clear communication between system parts. Mastering these debugging fundamentals can help prevent similar failures in the future and make systems safer and more reliable.